When we turn on a light switch, the light goes on immediately and starts to shine, while electrical current starts to flow through the wire. The electrical energy reaches the light bulb traveling with a speed of almost the speed of light. But the electrons inside the wire, which are carrying the electrical current, are moving slow, extremely slow. It would take hours for the electron to reach the light bulb. So how does all this make sense? For more science videos, subscribe and hit the bell. Materials in which electrical current can flow are called electric conductors. Different from other materials, conductors have 1 to 2 free electrons, which are weakly bound to the nucleus, and therefore can move about freely within the conductor. When the switch is off, the free electrons are not still standing. Due to thermal energy, they are constantly moving and colliding with other electrons and atoms, and so changing directions. But if we look at a cross-section of the conductor, the sum of electrons that pass through the cross-section in one direction is in average equal to the sum of electrons that pass through in the opposite direction. Therefore, the average net velocity is zero, the charge is balanced and no current flows. When we turn on the switch, an external electric field is established through the conductor. This field accelerates the electrons in the opposite direction of the field because the electrons are negatively charged. The thermal movement is more dominant than the movement caused by the electric field, so you would not see a big difference. However, when we look now at the cross-section, more electrons would pass through one side, which means that electric current flows. Electrons don't really physically collide with each other. They have own electrical fields with which they affect other electrons by pushing them further away, and due to this, electrical effects move much faster down the wire than electrons itself. When we say that electrons are moving slow, we think of the so-called drift velocity. The drift velocity is the average net velocity caused by the applied electric field. This velocity depends on many parameters and it's different from case to case. For example, in a copper wire with a radius of 1 mm and a current intensity of 1 ampere, the drift velocity would be 23 micrometers per second, which means that the electrons would move about 1 meter for approximately 12 hours. For an alternating current, the electrons would move even less. They would oscillate together with the voltage oscillation. The electromagnetic energy, however, flows overwhelmingly outside the electric conductor. Therefore, the purpose of the conductor is not to conduct electric energy. Its purpose is to guide the energy-carrying wave, so the wire is a form of a waveguide. The speed at which electromagnetic effects travel down a wire is called the signal velocity. This signal traveling down an electric cable is affected by its interaction with the materials in and surrounding the cable. The signal velocity is therefore smaller than the speed of light, and it varies between 50 and 99% of the speed of light, depending on the cable type and surrounding insulator, but it is typically close to the speed of light. It is important to know that the electromagnetic field does not move through space. The field is a property of the space. The electromagnetic energy is the one that moves. The corresponding field simply grows and declines in response to the energy flow. The electrons, which are distributed all over the conductor, affected by the field fluctuation, which travel down the wire with a speed close to the speed of light, starts to move, and due to this, current flows. A good analogy for all of this is a large classroom with hundreds of students, which represent the electrons, spread all across, waiting for the class to end. As soon as the ringing of the bell, which corresponds to the external electric field fluctuation, reach the students, they start to leave the classroom. Shortly after the sound of the bell goes through the door, the first student leaves the room because there is always someone next to the door. Just few students can go through the door at once. Because of this, they are moving much slower than they could. This propagation corresponds to the drift velocity of the electrons. Because the students have to come home quickly to watch YouTube videos, they fidget nervously around and walk in place. This movement corresponds to the thermal speed. Although the students move much slower than the speed of sound, which corresponds with the signal velocity of the electric energy, the first students reach the door shortly afterwards, similar to the electrons in the wire. Ants can easily find the shortest way to their food. Check out this video here to find out how an ant colony manages to find the optimal path in a complex environment. And don't forget to subscribe and leave a like.